In this video, we'll continue our discussion on the idea of solutions by tackling the idea of solubility. This is one of the big steps we need to take before we can dive into the bigger idea, one of our three main reaction types, which will be precipitation reactions. We'll start with a quick rundown of the objectives of this video. First, we'll define what the term solubility is. Many people have a good idea of what this word is already about, but we'll talk about an official definition. We'll then tackle the concept of saturation. This is something you probably have seen back in biology classes, the idea of an unsaturated, a saturated, and a supersaturated solution. What will probably be new is dealing with something new known as a solubility curve, a graphical way of predicting saturation. And then last but not least, we'll talk about the idea of predicting solubility of an electrolyte in water. And this is going to involve using a table such as this one, known as a solubility table, or has solubility rules. Later on in the chapter, you're going to be responsible for knowing these solubility rules so that you can decide whether or not a certain ionic compound will or will not dissolve in water. So let's begin then with the definition of solubility. It's the ability to dissolve a certain solute into a certain solvent. If you recall back to our discussion on how things actually go about dissolving, it's the ability of the solvent molecules to pull the solute off the lattice, as well as the ability of the solvent molecules to encapsulate the solute molecules. These kind of things combined change as you change different solvents and different solutes, and as a result they alter the solubility of different substances. This solubility concept is dependent on the characteristics of the solvent and the solute molecules, and more importantly, we link it back to this idea, more importantly, how they interact. The stronger the forces are between the solute and the solvent, the more likely you're going to get a higher degree of solubility. A great example of this, we all know that table salt is very soluble in water. That happens to do with the table salt itself has charges and the water has charges. So we would say that this is very soluble. Whereas table salt in vegetable oil we would describe as insoluble. The vegetable oil does not have the same kind of charges that water has, and as a result its interaction with the sodium chloride is much weaker, and we get much less of the sodium chloride able to be dissolved. So now that we have an idea of what solubility is all about, we can talk about the amount of stuff that can be dissolved, and that topic is known as saturation. What saturation is referred to is the maximum amount of solute that can be dissolved in a certain solvent, and the key word here is the maximum. All solvent and solute combinations have a different maximum amount of solute that they can hold per unit of solvent, and again, that's our saturation value. And this is data that we can look up. And then the last thing we can say about this is this information is very often temperature dependent. And for most substances, as your temperature increases, your saturation of your solution increases as well, meaning we have a higher maximum amount. Now this is not true for everything, but again, for a lot of substances, this is the general policy. As temperature increases, we can dissolve more. If you've ever made candy, you can increase the amount of sugar you can dissolve in water simply by heating the water up on a stove. So this leads us then to another couple definitions that you guys should already be pretty familiar with. We can describe solutions in a couple different ways then. The first one we can talk about is a saturated solution. You have dissolved the maximum amount of solvent per unit. Any more solute that you try and add to your solution will remain undissolved. It'll float to the bottom. Likewise, a solution can be unsaturated. In this scenario, you have dissolved less than the maximum amount of solute. If you add more solute in this scenario, that solute will then dissolve into the solution, increasing the concentration. Last but not least, and this is always the strangest of the group, we have a supersaturated solution. Whenever you see the prefix super, that usually means more, and that's exactly what the definition is. In a supersaturated solution, you have dissolved more than the maximum amount of solute. And I put a question mark on the end of this, because why use the word maximum if we can dissolve more than that? Well, this maximum, again, is temperature dependent. So you can cheat the system a little bit by simply increasing the temperature, dissolving things to a saturated point at that higher temperature, and then reduce the temperature back down again. And without any kind of triggering force, the extra dissolved stuff will actually stay in solution. So that's how you end up getting a super saturated solution. These two guys happen very quickly and naturally, saturated and unsaturated. Super saturated usually requires some purposeful steps to make a solution in this kind of condition. Now, if you want to determine the saturation of a solution, you're going to need something like this. And this substance, or this diagram right here, is known as a solubility curve. Typically, when you're dealing with a solubility curve, it has many plotted lines. Each plotted line corresponds to a particular chemical compound, and what it shows you is the saturation point of that compound at different temperatures. So what it plots is the amount of solute that can be dissolved per 100 grams of water, and it usually says that right over here on the side. And again, we can see that these things are temperature dependent. As the temperature on the x-axis increases, we see most of the graph lines slope up, which is what we said before, with a couple examples like the cerium sulfate down here sloping downwards, and even sodium chloride, which actually stays pretty level throughout the process. We don't get a lot more sodium chloride dissolved in water simply by increasing the temperature. So the way we can interpret this graph then is where you are in relationship to the line. So if we focus on this sodium chloride line here, and I'll get rid of some of this text here. If we focus on the sodium chloride line, which is this blue line, and then we say we're at 50 degrees Celsius, if I've dissolved, say for example, 20 grams of salt at 50 degrees Celsius, so the way we go about using a plot like this is simply by interpreting where you are with your solution in relationship to the line you're dealing with. Say, for example, we're dealing with the substance sodium chloride again. We would highlight this, and we're going to focus on the blue line for sodium chloride. The other lines aren't relevant when we're dealing with this particular substance. So we can have different scenarios here. For example, if you have a situation where your solution is on the line, let's say, for example, you have 40 degrees or 40 grams of sodium chloride dissolved in your solution at 90 degrees Celsius, that would mean you have a saturated solution. This line represents the maximum amount of solute that can be dissolved at any particular temperature. Likewise, say you only have 20 grams of your sodium chloride dissolved at 90 degrees Celsius. That's below the line, making it an unsaturated solution. And then obviously if you're above the line, then say we got 100 grams of sodium chloride to dissolve in solution at 90 degrees Celsius, that would create the super saturated situation. So again, looking at where the line is and reminding yourself that the line, maybe we'll write this down, equals saturation. If you keep that in mind, being above the line means above saturation, supersaturated. Being below the line means less than saturated, unsaturated. And being on the line means a saturated solution. So let's talk about a couple of quick examples. I'll do one of these together just to give you an idea of what we're talking about, and then maybe you can try a couple of these on your own. Let's say, for example, we try to dissolve 100 degrees of sodium nitrate at 20 degrees Celsius. Well, let's plot a point that involves these two data values, 20 degrees Celsius, which is right here, and 100 grams of our substance. We're right up here at the top of the chart. We also need to identify which line we're looking at in this case. It's the sodium nitrate line, which is this line right here. If you'll notice in this situation, our point is above the line, meaning this is a super saturated solution. Take a minute, pause the video. I've got a couple more of these for you to take a look at. In a couple seconds, we'll go over the answers to these, and we'll see how you did. So let's take a look at the work that we did here. I got a couple answers for you. If we look over here, we have 100 degrees of sodium nitrate at 40 degrees Celsius. I made a point way up here showing that. The sodium nitrate line is this line right here, just like it was in the previous problem. And notice if this line were to continue up here, we would be below it, creating an unsaturated solution. Moving onwards, 30 grams of KCl. Here's the KCl line right here in the middle. 30 grams at 10 degrees Celsius puts us right on the line, creating a saturated solution. And last but not least, we take that same solution, but we raise it up to 60 degrees Celsius. Notice now we are below the line, and as a result of that, that creates another unsaturated solution. Really what this boils down to, if you haven't already figured it out, is looking at this plot and simply interpreting where your solution is in relation to the line that goes along with your particular solute. So that brings us into the final part of the discussion here, getting a little more technical with this idea of solubility. We're going to be introducing something called solubility rules. And basically what these are rules for determining which ionic compounds will or will not dissolve in water. This is a way of generalizing a lot of complex information, thousands and thousands of different substances, into a very small set of rules that we can work with pretty reasonably. And that's what I was saying here. It's a summary of the observations on the solubility of a bunch of different combinations of cations and anions in water. So basically all the different salt possibilities we have, and we can summarize in a quick table whether they will or will not dissolve in water. This makes our job a lot easier. It takes the idea of grouping and categorizing things to classify millions of compounds as soluble and insoluble without having to memorize the solubility of millions of individual compounds. So it's a way of getting through some work a lot quicker. What these rules generally show up in is big tables such as this one. What you should probably do is find a copy of these. I have this particular one down below on this page. If you pause the video and you can download it, you'll definitely need this over the next couple of days. But they come in lots of different forms. All of them say pretty much the same information. They're just formatted a little bit differently. We're going to talk in the next slide about how to go about using a table like this, and then you guys will get a little chance to practice it as well. But the basic way that they're structured is we have a list of compounds that are soluble and a list of compounds that are insoluble. For example, it's telling us that all compounds containing the nitrate ion are soluble, and then over on the right here it talks about exceptions to that rule. So I guess what we should say here is this is the rule and these are the exceptions. So if we see there are no exceptions for a nitrate, but if you're iodine, like this substance down here, compounds containing the silver ion with iodine are an exception. So if iodine compounds are soluble, the exception means that silver iodide, mercury iodide, and lead iodide are insoluble. So these are exceptions to the soluble rule. Same thing's going on down here. Phosphate compounds are generally insoluble, meaning they do not dissolve in water, unless they're paired with ammonia, which is one of our polyatomic ions, or the alkali metal cations. And we should maybe note on here, these are the elements in group 1 on your periodic table. We'll be talking more about these different metal group names later on in the year. So what I have here is a list of a bunch of different compounds. Your job right now is to take that table, you should already have one saved, and then use the rules listed on that table to figure out whether each of these compounds is soluble or insoluble. Take a couple minutes on your own to work through this, pause the video, and I'll have some answers on the next slide. So here's the answers we have going on here. We'll go through just a couple of these really quickly. We already talked on the previous slide, and your rules tell you that all nitrate ions are soluble with no exceptions, so that makes this compound soluble. You're also told that all sulfate ions are soluble, which makes the lithium sulfate soluble, but the sulfate ion does have some exceptions, and barium, if you look on your sheet, is one of them. When barium is paired with the normally soluble sulfate ion, it creates an insoluble combination, and that's what makes this substance insoluble. Phosphates, again, are considered insoluble most of the time unless they're paired with one of our alkali metals or group 1 metals, and that's the case here. So this is the exception pairing with sulfate, making this a soluble substance. Phosphate here is, again, generally insoluble. Scandium is not one of the exceptions, which makes this compound soluble. And last but not least, chlorine and the halides in general are make soluble substances, and again, iron's not one of those exceptions, so this guy is soluble. Overall, using the table isn't very difficult to do, but in the beginning it can be a little complex. There's a lot of rules to juggle. Once you get more familiar with those rules, I think you'll find that these types of predictions get a little bit easier. So that's pretty much it. At this stage in the game, you should be able to define and discuss what the concept of solubility is. You should be able to determine if a solution is saturated, unsaturated, or supersaturated using a solubility curve. And last but not least, using your solubility rules, you should be able to predict whether a solute, an ionic compound solute, will be soluble or insoluble in water. In class, we're going to get a chance to practice a little bit of these. I have a lab activity you guys are going to do, and hopefully by the time we get to the end of that, you guys will be pretty comfortable with this idea, which will lead us into our next major lab report.